All right, let's get started. We have a big crowd here, looks like. But that's, yeah. Anyway, let's get started on the talk on time. In case you're wondering what the talk is about, think of it, before we start the talk, think of a scenario like this. Let's say that you're sitting in a branch office and then in California, and then you're trying to copy, let's say, a DVD image or a CD image from your data center in New York. Normally, you would use a tool, Copy or Xcopy or Windows Explorer or something of that sort, and then you initiate the copy, and then most of you, I'm sure, would just go down, have a cup of coffee or something, and then come back while it's done. That's the experience which people have had in the past regarding transfer of data over wide area networks. So in this talk, I'm basically going to try to address some of the bottlenecks we've seen and some of the changes we have made to the system, and going to provide you tips as to how to improve your applications to best utilize the network resources. So good afternoon, and I want to welcome all of you to this third day of the PDC, and thank you all for taking your time out and coming, listening to me. I'm Matthew George, and I'm a software developer working with the File Access and Distribution group in Microsoft. Our group owns all the remote file access protocols in Windows. And the core file sharing protocol which Windows uses is SMB or CIFS, as most of you may know. And recently we've added SMB2, starting with Windows Vista, which addresses a lot of these things which we're going to talk about here. So this is a rough outline of the talk. First we'll look at why file access over WAN is such a big deal going forward. And then we'll look at two examples to try to illustrate where the problem lies and what are the problems. And then the next two bullets here, the improvements to the platform and application guidelines, they're not necessarily in that order. But I'm going to take two classes of applications. The first one I call throughput-oriented applications, which is effectively, what you want to do there is basically move as much of data from point A to point B as quickly as possible. And the second class of applications I want to talk about is the so-called interactive applications. They are UI applications or any other sort of interactive applications and how to optimize those. And then we look at a few general considerations. So I'll be talking about platform improvements as well as guidelines to applications so that you can most effectively use the Windows APIs to do your data transfer. So why do we care about accessing files over a WAN? So as you might have heard, one of the biggest trends in the industry, especially in the enterprise space, is data center or server consolidation. And specifically, I'm interested in, for the purposes of this talk, storage consolidation, which basically means that people are moving their file servers or the data stores from the branch offices to data centers. And once you have data centers, you also have the issue of moving large amounts of data from data center, say, on the West Coast to the one on the East Coast. So there's a lot of data center to data center traffic, file traffic, that you're interested in. And during the last 3 days of the PDC, I'm sure you heard a lot about cloud storage and cloud computing and stuff. So even in a cloud storage scenario, your data is actually going to be stored somewhere on the cloud, and you get to access your data over a WAN. Now, the trends driving storage consolidation, WAN bandwidths, they're increasing pretty rapidly. And the cost per unit bandwidth is coming down also pretty rapidly. So accessing data over a WAN is no longer as much as a deal as it used to be like 10 years back. So it's definitely possible now, given the current cost structure, to access data over WAN link. And in terms of the other benefits, you get better resource utilization, you get centralized management of your data, and so on and so forth when you keep data in the cloud or in a data center. Now let's see what I would classify as a WAN-friendly application. Well, bandwidth still costs money. Most people still pay for WANs based on the amount of data they transfer. So WAN bandwidth usage is still valuable. And one of the concerns, one of the key things about a WAN-friendly application is reduced bandwidth usage. And chatty applications can lead to very long end-user wait times. So if in doing an operation X, let's say that it involves 10 round trips to and from the server, it's going to take a lot of time over a WAN. So you want to reduce the chattiness of your applications. And the third important thing is that applications which were designed for running over a local disk, like your C drive or D drive on your local computer, when you automatically run them over a WAN, you get into the programming models used will end up causing hangs or delays in your application. So this is something which you want to address when you write applications. And typically, within Microsoft, we use 5 seconds as a typical guideline. If something hangs for more than 5 seconds, somebody is very likely to press the X button and kill off your app. So a hung app is pretty much as bad as an app which crashes on you. And then some reasons why you should change your applications. This assumption that app file data is local is no longer true. And even if you want it or not, people are going to run your applications and access data over a WAN. So it's very important that we are aware of this. And then we have made a lot of improvements to the platform, starting with Windows Vista and then going forward to Windows 7. And once the platform is improved, a lot of the bottlenecks in the application become quite apparent. So it's important. And we have made changes to the behavior of APIs. So if your app is using them incorrectly, you would need to change apps. And these are just ballpark numbers. What kind of gains can you expect? For throughput-oriented applications, you can expect anything from 2 to 10x. We have seen much larger gains for some scenarios. So these are just ballpark numbers. And then 30% reduction in traffic, and similarly 30% improvement in response time you can see if you adopt some of these techniques. Now let's try to look at the problem. We'll try to see what a few aspects of the network first to understand why we have these problems. So the first thing I want to talk about is bandwidth or throughput of the network. It's fairly obvious. It's the amount of data you can transfer at any in a unit time. And then you have the round-trip latency. That's the time taken for a request to go from a client to a server, and then for the response to come back. That's the round-trip latency. And an important parameter here is a product of the bandwidth and the round-trip latency. That's called the bandwidth delay product. It's a very important measure. And here is an example. You have a 100 millisecond link of throughput 100 megabits per second. And you multiply those two, and you get 10 megabits, which is roughly equivalent to 1.25 megabytes. And network utilization is what you want to maximize when you're talking about throughput-oriented applications. You want to maximally utilize the network. Now, if you have the bandwidth delay product and you know that your application posts a certain amount of data, the maximum theoretical utilization you can get is basically the amount of outstanding data divided by the bandwidth delay product. So as an example, for the above network, where you have a bandwidth delay product of 1.25 megabytes, if your application posts just 64 kilobytes of data on the network, you're going to get at most 5% utilization of the network. So it's something to be aware of. So these are just some numbers from within Microsoft. We have data from branch offices to Microsoft data centers. And these are the typical latencies and the bandwidths you can see. So typical bandwidth in the US is about typically less than 100 milliseconds. So a mean is 108 milliseconds. And then you can see bandwidths anywhere from 10 megabits to all the way up to 1 gigabit. Let's take a quick look at the file I/O stack. So I'm going to specifically focus on SMB, SMB to the Windows. These are the core protocols used by Windows. So we'll look at the SMB file I/O stack. The SMB protocol, it's a very old protocol. It was designed by IBM back in the 80s, and it really hasn't evolved much. And as networks have improved, the protocol has pretty much remained the same with minor improvements. So the original SMB or CIFS protocol has a lot of limitations running on high BDP networks. And with Vista, we introduced the SMB2 protocol, and one of the design goals was to make it run well on high BDP networks. So you have changes at the protocol level. And the other important thing to note here is the cache. So you see two caches here, so the client cache and the server cache. For the purposes of this discussion, we are mostly focusing on the client cache, because any data that's satisfied from the client cache basically eliminates a network round trip. So we are focused on the client cache there. And the SMB redirector is basically the file system sitting on your Windows box, which takes the Win32 API calls to read, write files, and then send it out over the network. And this is a brief overview of the Win32 file I/O API. So you have synchronous versus asynchronous API. So asynchronous APIs are also called the overlapped APIs, if you're familiar with Win32. And even those people who are doing managed code, you have pretty much all the equivalents in the managed world. So you have overlapped or asynchronous I/O in the .NET land. And then you have cached versus non-cached I/O. Non-cached I/O just flows directly to the server. It doesn't hit the client or the server cache. And then another important concept is handle-based versus path-based APIs. We'll talk about this later in the talk, but just keep this in mind. And then you have APIs to cancel I/Os. I/O cancellation was never a very important thing when you're talking to a local disk, because they complete fast, so it's not a big deal. But when you're talking over a WAN, cancellation of I/O is very important, and your app must support it. Let's take a look at two problems. Copying a large file I talked about earlier. This is a 20 MB file copy over a 100 milliseconds and 1 gigabit link. This was done on Windows 2003 because we have done optimization since then. So this is just to get a feel of what it is to do this on Windows 2003. It takes about 38 seconds to do the copy. The link bandwidth delay product is about 12 megabytes. That's the product of 1 gigabit per second and 100 milliseconds. And the throughput, 20 megabytes divided by 38 seconds, you get about 4.2 megabits per second. And as you can clearly see, the utilization is pretty bad. It's 0.42%. The network is just idle. It's mostly idle. It's not doing anything. And this is a task manager graph of what the network utilization is. And you can see it's right above 0.5% while copying the file. What is the reason? The copy file API, which is the API used by most of the copy tools on Windows, on Windows 2003, it posted just a single 64 kilobyte buffer onto the network. And as you can see, the maximum theoretical utilization you can get is about 0.53, because 64 kilobyte by the bandwidth delay product. And the actual utilization you see is somewhat less than that because of additional overheads. So this is clearly a very inefficient way to transfer data. Second scenario is a kind of an interactive app. Let's look at opening a Word document, Office 2003. Again, they have made changes to Office 2007 to address some of these limitations. But the same link, 100 milliseconds, takes about 23 seconds to open a 300 kilobyte file. And if you look at the network using a sniffer, it's about 1,200 to and fro frames out on the network very inefficient. And you can see if you analyze the frames on the network, the same file is being opened and closed several times. The same data is being read and reread from the server several times. And you also see a lot of non-data traffic to get attributes of the file and various other things, metadata traffic. And the metadata traffic is about 30 to 40%, I believe, in the sniff. And the reason is that due to the behavior of Windows 2003, Windows Explorer and Office running in parallel, SMB loses its ability to cache data. That's because of the interaction between Windows Explorer and Windows Office 2003, as well as the way Office 2003 behaves. We'll talk about this in more detail. Now let's see, for high throughput applications, what are the improvements we have made to the platform. So as I said before, we did the SMB2 protocol. And the SMB2 protocol was designed with the high bandwidth delay products in mind. So it can definitely support a large number of outstanding operations against the server. It also supports large buffer sizes. So SMB1 had a lot of limitations as to what buffer sizes could be used. But SMB2 is much more generous in that regard. So it can use larger buffer sizes. It can support deeper pipelines. And then if you issue a large I/O request to the SMB2 stack, it has the ability to split it up and then pipeline the individual chunks in the most effective way. So the best way to utilize the SMB2 stack is to issue large I/Os. We also have had changes to the TCP/IP stack, again, starting with Windows Vista, and then we have had incremental changes for Server 2008 and then Windows 7. TCP supports very large window sizes, which are required in such networks. And finally, we have changes to the cache manager and file system components to support, to efficiently support large I/O sizes. Now, I talked about the copy file API. This is one of the key APIs which a lot of applications as well as tools use. And this is used to transfer data. We have made huge changes to the copy file API, starting with Windows Vista, and then it was refined in SP1, and there are more changes upcoming for Windows 7. Copy file earlier used 64K chunks, as I mentioned before, and now it uses 1 megabyte chunks. And instead of 1 I/O at a time, it uses 8 I/Os at a time. So it issues 8 I/Os and then waits for the first one to complete, and then so it pipelines 8 I/Os. Now, all the inbox tools, which you might be familiar with, Copy, RoboCopy, Xcopy, even Windows Explorer, they all use the copy file API. Now, you can see the difference here. So there are 6 set of lines in this graph. So the lowest 2, they're from Windows 2003. That's a scenario which we talked about where you get 0.5% utilization. So with Windows 2003, even on a LAN, you don't get very high throughputs. This is a gigabit link, and you get less than 100 megabytes a second. And if you're talking about a 40 millisecond WAN, it's almost like near zero, the throughput. If you go to the 2 lines above that, that's Windows Server 2008 and Vista SP1. Huge improvement there. So we made changes there, and it's not fully up to the mark, but you can see it's probably about a 50 to 100x increase in throughput there for higher latency especially. And then we have been tweaking both the network stack as well as the file system redirector. And after all these tweaks, now we have a final set of numbers, which and these will be released as patches or incorporated into Windows 7. But that's almost like the ideal line. So you get maximal throughput irrespective of your latency. You're getting all your gigabit throughput irrespective of the latency on the network. So that's a huge improvement, probably 200x improvement, I would say, compared to Windows 2003. Now let's look at guidelines for applications. Well, used overlapped or asynchronous I/O whenever possible. So most apps use you issue a read file call or an fread call, or in C# .NET land you again use a file stream class and do a read call, and it's synchronous. Now you open the file with this file flag overlapped option. I'm talking specifically about the Win32 APIs, and there are equivalent options in the .NET APIs too. And the read file, write file, and the device I/O control calls do support overlapped I/O. So the key thing is you open the file using the file flag overlapped option, and then use the read file and write file APIs, and you can issue as many I/Os as you want, and then eventually you wait for completion of these APIs using the get overlapped result. Another option is actually to use the EX versions of these APIs. So you have read file EX and write file EX. They even support a completion callback, so it'll call you back when the operation is done. And if you want even higher throughputs, you can use completion ports. So if you look up MSDN, you'll see completion queues and completion ports. So these give somewhat higher throughput. And the important thing to remember is that if you want to maximize your network utilization, issue as many I/Os so as to fill the network BDP. So if you have a 12 megabyte bandwidth delay product, you want to issue 12 megabytes of I/O. You have to have 12 megabytes of I/O outstanding so that you get maximum utilization. And one thing to remember, this is not always applicable to all applications, but for very throughput sensitive applications, it sometimes helps to disable the caching on either side, because pass through the cache manager sometimes can add up, incur delays in the I/O. So if you want very high throughput on like a server to server transfer, it's sometimes better to disable caching on both sides. And there are options in the create file API to disable buffering, file flag, file no buffering, no intermediate buffering. And these steps actually help both SMB2 as well as local I/O. If you're doing I/O to your local disk, it helps. And this is an illustration of unpipelined versus pipelined I/O. If you do a synchronous read file or write file call, you transfer the data and then you wait for the response. It'll be a long wait. And at the same time, you pipeline it, you can see the effect on network utilization. You're constantly pushing data through the network. So the second important thing is to use large I/O sizes. It clearly implies that there are fewer passes through the file I/O stack if you issue a larger, and it also gives the opportunity for the file system to segment it appropriately and then send it out on the network. One caveat to remember here is if you are targeting your applications for down level Windows 2003 SMB1 scenarios, large sizes don't work well because of certain implementation deficiencies. So there a 60K chunk for read and 64K chunk for writing is ideal. But with Windows 2008, Vista, and higher with SMB2, issue I/O size is about 1 megabyte. That's what we have observed is the best size, 512 to 1 megabyte. And don't go too large because there are resource constraints, because if you do an I/O with a really large buffer, the system actually has to lock down those pages and map them to kernel space. So you can run out of resources pretty fast if you do very large I/O. So more than 16 megs, not recommended. And then use the copy file API for large data transfers. If your app needs to transfer data from server to server, use the copy file API because it's well optimized. We have tweaked it for over 3 years now, and it's pretty much giving us the maximal throughput now. And Office 2007 actually uses copy file. So when you edit a document located on a remote server, it actually copies a file over locally, edits it, and then copies it back, because they found that that was giving more gains than trying to operate on the file online. And a copy file by definition is a synchronous API, so it waits until the file is copied. So if you have multiple small files, just multi-thread it and issue several instances of the copy file API on several threads. And Windows 7 Robocopy is a fairly popular tool among power users and administrators. So we are adding a multi-threaded option to Robocopy, so you can now specify the number of threads, and it will spawn up several instances of the copy at the same time, and that it speeds up process by a significant amount, actually. Next one, if you can't change your app to use large IOs, asynchronous IOs, try to make use of the cache manager. Try to make use of caching, because if you're doing small IOs, you let it run it through the cache, and the cache manager will actually issue larger IOs down to the network, and then it will satisfy your small IOs from the cache. So use the cache manager whenever you can. It can also hide delays with slow disks. If you have a really slow IDE or SATA disk, using the cache can sometimes help you hide disk latencies. And provide hints to the cache manager when you open the file. So if you're accessing the file sequentially, you can use a file flag sequential scan, which allows the cache manager to actually read ahead of you. So when you read the data is probably already in the cache. So use the hints. Minimizing extending writes. A lot of applications normally append to the end of a file. It's a very normal thing to do. And remember, there's always a cost to appending to a file. For the purpose of this talk, appending to a file, if you extend the size of a file, that operation becomes synchronous. Even if you wanted it to be asynchronous, it's going to become synchronous, and it happens one at a time. So if you want to append to the end of a file in a high-performance application, set the size of the file to a much larger value, and then write. It's much, much faster than writing smaller chunks. There are other factors there, like disk fragmentation and stuff, but we won't go into those. This is a very important thing. And using these flags with create file flag write through. This results in all your data being flushed right into to the disk before the write completes. So it incurs cost. And flush file buffers. You can issue this call on a handle, and system will take care of flushing out all the data for that file. But an unintended side effect is that most of the disks which are there today, they don't have a logic to distinguish between data belonging to file X or file Y. So when you issue this call, it's essentially asking the disk controller to flush all the data and cache to disk. And these days, IDE disks have like 16 to 32 megabytes of cache, and it's fairly significant cost there. So use this API, flush file buffers, sparingly. Now those are the guidelines for the high throughput apps. And let's look at the second category of apps. Those are interactive or applications where response time is important. Let's look at the Windows I/O model. There are some concepts here which we need to understand before we look at the actual issues. The Windows I/O model supports two forms of I/Os, handle-based I/O and path-based I/O. Handle-based I/O is everybody uses it. You open the file, you read, write using the handle, and then finally you close the file. Path-based APIs, they just take a path. For example, get file attributes. You give it a path name, and it goes fetches the attributes for the file. But remember that underneath the covers, this involves opening the file, querying the attributes, and then closing the file. So it involves 3 separate steps. And if you issue these individual steps over the network, that's 3 round trips, at least 3 round trips. So you issue a get file attribute call. Instead of 1 round trip, you are effectively getting 3 round trips to the server, first to open the file, then to query, and then to close. So it's very important to understand that these path-based APIs often have additional cost associated with it. The second key thing with respect to responsive applications is caching. So the more data you satisfy from the client cache, the more responsive your app, the less network round trips you have, and the more responsive your application is. And when we talk about caching, we have 3 forms of caching effectively. The first is data caching, which we all know about. So read caching is caching data which is read from the server, keep it in the client cache, and then serve it out to applications later. And then write caching is basically writes done by the application are temporarily stored in the cache and then lazily flushed out to the server. So that's write caching. And when you do the Win32 file I/O, by default, caching is turned on. So whatever data you read is cached, and whatever data you write is actually just cached. It's not actually sent to disk immediately. It'll be lazily flushed out to disk. The second form of caching we are interested in is metadata caching. These are non-data attributes related to a file. So file attributes, your file time, file sizes, even directory enumerations can be cached. And our SMB client does cache all these things. We'll talk about it. And the third thing is handle caching. That's a very, I would say, strange concept. It's basically the SMB client or the SMB redirector holding a handle open even after the application has closed it. So let's say that application opens a file, does some I/O on it, and then closes it. The SMB redirector actually does not send the close over to the server. It will keep the handle in the hope that if the application comes back and tries to open the same file again, it can just reuse the same handle without sending a create. So handle caching is also done by our SMB client, and it's very useful in some scenarios. Yes?
Is this with SMB2?
Both SMB1 and SMB2 do support handle caching. Now, why doesn't, as we saw in the Office example before, why doesn't caching work very well? Because we saw that the same data was being read again and again from the server, and the same file was being opened multiple times. Why didn't caching work? The reason is that when you talk about a network file system, in addition to the normal caching semantics, you need to maintain cache coherency. For example, if there are several clients accessing the same file, you need to make sure that if all the clients decide to cache the data, you need to make sure that they are coherent. Basically, if one client makes a change to the file, you need to invalidate the caches on all the clients. So there's additional overhead or additional protocol involved in maintaining the cache. Now, SMB uses what are known as opportunistic locks or op locks to do the caching. And these are completely hidden from the application. And a lot of people actually confuse file locks with op locks. They have nothing to do with each other. And op locks is basically just a cache coherency protocol, which SMB uses. That's it. Now, op locks are granted by the server, and it tells the client what kind of information it can cache. Now, you have with SMB1 and SMB2, as implemented in Vista and Windows Server 2008, you have two levels of op locks. The first is what we call as a batch op lock, which allows the client to cache reads. It can cache writes, as well as it can cache the handle. And this is an exclusive op lock in the sense that only one handle can have a batch op lock. The moment you open a second handle to a file, you lose the op lock. You lose the batch op lock. And the advantage of this is that the client can continue caching data even after the application has actually closed the file. So let's take a scenario where app opens a file, reads data, and then closes the file. Then it again reopens the file, reads data, and closes. If you have this sequence of operations, the batch op lock helps because after the app closes the file, the redirector caches the handle as well as the data. And the second time it opens it, it just reuses the handle. You won't see any more network traffic. It will just serve the data from the cache and keep reusing the same handle. In fact, this term came from the way batch files operated back in the DOS days, where the system actually executed a batch file by opening the file, reading one line of it, closing the file, and then executing that command. Then it reopened the file and then read the next line and then closed it and then executed the next. So this was invented, I believe, to optimize batch file. That's how the name batch came about. And the second level of caching which we have is level 2, This basically grants the client ability to cache reads. And this is shared because as long as everybody is reading the data, a lot of clients, a lot of handles can have a level 2 op lock. And the key deficiency with the level 2 op lock is that it does not allow handle caching. So as soon as the app closes the handle, the redirector has to close down the handle. And closing down the handle means you lose the op lock, and you have to lose data caching too. So that's what is the second point I mentioned here. The client cannot cache data after the app closes the handle. So if you have a scenario where multiple clients are accessing the same file, and you have only a level 2 op lock, the moment the clients close the file, you lose the cache too. So that's one of the biggest drawbacks of the level 2 caching. And op locks are revoked by the server when somebody tries to modify the file or opens the file. This is a quick sequence diagram illustrating how you can lose data caching. And this is not even talking about 2 different clients. It's the same client. The thing to remember here is that op locks are based on a handle. So the system does not know whether 2 handles on the server side come from 2 different clients or on the same client. So let's take example here. You have an app which opens a file for read and write. These are Win32 APIs. I'm sure you can translate it into the .NET equivalents here. So the create flows to the server, and the server grants, let's say nobody else is accessing the file, it grants a batch op lock. Client reads data, the read goes to the server, and the data is cached on the client because it has a batch op lock. Now let's say that the client closes the handle. Now the close does not go out to the server because you have a batch op lock. You save a frame there. Now let's say that the client opens a file again with the same access mode. So you have a generic read, generic write. It's identical to the first open. So the client can just reuse the first handle. And well, you save one frame there, and let's say it wrote some data to the cache, to the file, and data is just written to the cache. Nothing goes out to the server. Now let's say that the client does a second open while this first open is active. What happens is that we cannot use the same handle because this open is different. It's a generic read. It does not have the right option, a right flag on it. So the server actually breaks the op lock because it's a second handle on the same file. And as a result of breaking the op lock, you lose the cache. So the client flushes out the cache data which it wrote earlier, and then it tears down the cache, and then the create completes. And now let's say that it does a write. There's no more caching, so now your write goes out on the wire. So this is a classic case of 2 apps, or even the same app, opening 2 handles to the file and causing SMB to lose caching. So once you are in this situation, at the end of the sequence, you lose caching on the file, and every I/O is going to the server. So it gets really expensive. Now, yes?
On that slide, are you talking in the context of going through the SMB as opposed to opening a raw socket?
Yes. Let's look at changes we have made to Windows 7 to better support caching. So we analyzed this problem quite a bit, and we found that almost a lot of the modern applications, applications are no longer simple. And they often behave very unpredictably. Basically, they are very complex in the sense that they open multiple handles, they have multiple paths of execution, they have concurrency. So it's very hard to exactly define what an application does. So we decided to change the protocol, change the file systems to allow these application complexities. And we introduced what is known as SMB2 leasing. It's basically an enhancement to op locks, and it allows better caching semantics. And it can support existing applications, and it can mitigate cross-application interference, like, for example, between Explorer and Office, the scenario I talked about, both of them opening the same file and trying to read data out of it. And with the leasing scheme, we can allow full caching as long as all the handles come from the same client. So there's a concept of a client which is introduced here. So as long as all the opens to the server are made from the same client, you can retain all your caching, and as a result, you save a lot of network traffic here. And in addition, we added a new lease level which allows read and handle caching. So if you look at the level 2 op lock, it allowed only read caching. It didn't have handle caching. So this is a new level which allows multiple clients to hold on to cache data even after the apps close their handles. So this is a shared lease. It can be held by multiple clients, and it allows the clients to cache the reads as well as handles. And as a result, the cache can live even after the app closes the file. This is the same sequence diagram with leasing. One client, one server. You open the file, so one round trip to the server, and server grants a lease. And you read data. Data is cached. Now you close the handle. Close does not go out to the server because we have the handle caching capability, so you can keep the handles. And then you do a second create file. We can reuse the same handle. You can write to the file. Data is written to the cache. It doesn't go out on the wire. Now let's say the app does a second create. It's different from the first one in that it's just generic read. Now this create has to be sent to the server because you can't reuse the first handle because the access modes are different. Even though you send it to the server, with the leasing model, since both of these arise from the same client, you don't lose your lease or you don't lose your op lock. So as a result, you still continue to cache. You have two handles. Now if you write data using the second handle, using the first handle, still in the cache, no harm. And you can see, compared to the previous scenario, why this one is significantly better. So irrespective of what the application does, in most scenarios, we are able to effectively cache data. Now, these are two more new features which we added with Windows 7 and Windows 2008, Server 2008 R2. These are not directly related to the caching I just described. Think of it as secondary caching on the client. So if you've used Windows Vista or even XP, there's this feature called offline files or client-side caching. It's basically, think of it as a level 2 cache on the client, which is persisted onto disk. So you have the in-memory cache, and think of this as a level 2 cache, which is on disk. So potentially your cache can be larger, and it can persist across network disconnects too. Now we are extending the offline file cache to actually augment the client's in-memory cache. So you have access to a larger cache, and we don't enable it. We don't want to enable it all the time because the additional cost of writing to your local disk and reading data from your local disk can sometimes be expensive, especially when you're running over LANs. So this feature is actually turned on can be selectively turned on only when your network latency is beyond a certain threshold. And this enables a larger cache on the client. The second interesting one which we're doing for Win 7 is the branch cache. People also refer to as the peer cache. This is specifically for deployment in a branch office. Now, let's say that there are several computers in a branch office trying to access files from the data center. Let's say that it's the same set of files. Now, this branch cache allows, it creates a distributed cache among peers in the branch office. And then when somebody else in the branch office tries to access the data, it will rather fetch the data from another computer in the same branch, another peer in the same branch, as opposed to going to the data center, going to the server. And it uses hash-based technology. These hashes are generated by the server, and that's how these data blobs are looked up on the peers. So this is another enhancement we are doing to reduce branch traffic on Windows 7. This is a quick illustration of the branch cache in action. You need, of course, Windows 7 server. That's also called Windows 2008 R2. and Windows 7 clients. Let's say you have 2 clients in your branch office and servers in your data center, and you have a file located on the server. Now, let's say client 1 accesses the file. You pull down the file from the server using SMB. And this client actually publishes this file in its peer cache. Now, let's say client 2 wants to access the same file. So before it goes to the server, it actually looks at its peers to find whether the required data is there. And if it's there, it will actually pull the data from its peers, not from the server. And now, let's say that another user on client 2 tries to access the same data. In fact, you don't even need to go to the peers. If you have the transparent cache on, this file is cached persistently on the client. So you can actually just get the file from the same client, from the disk of the same client. You don't even have to go to its peer. So this is branch cache and transparent cache working together in tandem. And we expect this to be hugely beneficial for a lot of branch office scenarios. This does not require any programmatic intervention. You just need to configure this via group policy or some other setting. So you get this for free. Now let's look at some of the guidelines for effective caching. We looked at the improvements to the platform. We looked at leasing and some of the other improvements. Now let's look at, from an application perspective, what we can do to improve the caching behavior. So the easiest recommendation I can give is avoid opening multiple handles. So if you're writing a new app, well, you can probably do it. Now, for existing apps, clearly this is not possible. So that's why we went with the platform changes. But if you're writing a new app, try to open one handle and do all your I/O. You can issue even attribute queries and other metadata queries using the handle. Now use the handle-based APIs if possible. The thing about path-based APIs is that, as I said before, it often involves opening the file, querying whatever is needed, and then closing the file. So it implicitly involves another open to the file, and this often can interfere with your op logs. So if you have a handle, use a handle-based API to get the desired result rather than using a path-based API. Handle collapsing is another interesting optimization in the SMB redirector. So you can, the SMB redirector has the ability to collapse identical opens to the same file onto the same server-side handle. So if 2 applications open the same file in the same way with exactly the same access mode and share modes and create options, in fact, the client has the ability to reuse any existing handle and just collapse both of them onto the same server-side handle without sending over a create to the server. And in the SMB1 case, this is particularly interesting because if you do not send a second open to the server, you are essentially preserving your op log, or you are essentially preserving your caching. So handle collapsing is an important thing to remember, and it's particularly useful for SMB1 as well as SMB2 on Vista and Windows 2008. With Win 7, it's not so much of a problem because even if you open multiple handles, you can still retain caching. Second thing, provide hints to the cache manager and the SMB redirector when opening the file. As I mentioned before, when caching is on, you want to provide hints while opening the file so that the cache manager can effectively deal with your I/O. So for example, if you are accessing the file sequentially, you must pass the file flag sequential scan flag to create file so that your cache manager will read ahead, and then it'll also keep the system responsive because it can immediately throw away pages which you have already read because it assumes that you're going to read forward on the file. Few other caveats. Write-only opens. Write-only opens, unfortunately, because the design of the caching in Windows cannot be cached, because when you want the cache manager to play a role, it needs to be able to page in the data before it can page out the data. So if you do a write-only open, you can't cache. So a lot of applications I know, I have seen it doing a write-only open and then issuing 1 byte writes. It's like really bad. Each write will flow out on the network, and you will see like really poor performance. So just do a read-write open, and you'll be good. Byte range locks also cause loss of caching, especially when you are sharing, when there are multiple people accessing a file. If you take a byte range lock on a file, if you lock a particular region of a file, you will lose caching. Now let's look at the next aspect of caching, that's metadata. As I presented in the Office example before, metadata queries are fairly significant. So approximately 30 to 40% of SMB data traffic is metadata. And metadata traffic usually can involve up to 3 round trips because of the path-based nature of the APIs. Now, SMB clients, the SMB redirector can cache metadata, but it's fairly limited. So for data caching, we have op locks to guarantee consistency among caches. But for metadata, there is no such scheme. So it's mainly opportunistic, or what you would call best effort. And they are very short-lived caches, and they expire after a few seconds. Now, SMB1 caches file attributes, can cache timestamps, file sizes. So if you do get file attribute calls on SMB1, you would often not see network frames because the data is cached. Now, SMB2 also caches directory enumerations in addition. So if you do a dir or anything which involves a directory enumeration, the directory enumeration is cached, and then you can satisfy directory queries from the cache subsequently. Now, key thing to remember, there are a lot of metadata APIs, related APIs in Win32. And to make sure we maximize the use of the metadata cache, we need to adhere to some of these guidelines. So get file attributes, get file size, get file time, they are all cached on all platforms. So these are good to use. Now, directory enumeration via find first file, find, these are the 2 APIs which you typically use for directory enumeration. SMB2 caches them by default, so these are good. Now, if you're using the get file information by handle EX call, this is a handle-based API. So given a file handle, you can query for metadata on the handle. And it supports various types of queries. And only these 3, file basic info, standard info, and name info, are cached. So if you query for anything else, you would get a network round trip to the server. So be aware that only these 3 are cached. Now, if you have to query, if your application has to query for information level which is not cached by the redirector, you certainly want to avoid repeated queries. So you want to cache those in your application. Use the get file information by handle API. This is a handle-based equivalent of get file attributes. So use this API if possible. And a lot of metadata queries involve variable length buffers. So it returns variable sized information. So very common programming practice we have seen is first make the call using a 0 length buffer, and it returns status more data, or error more data actually. And then it also gives you back the size of the buffer that's required. Now you make a second call with the appropriate size, and it gives you back your data. From a programming perspective, this is a neat thing, but when you're looking at the performance of your application, it's not a good idea because it involves 2 round trips instead of 1. So use a default, a reasonable buffer size at the right in the beginning for the first query, so that in most cases you would be 1 round trip to the server would be sufficient. Now, one thing not too many people know is you can use the get file information by handle EX API to enumerate directories actually. So the normal APIs to enumerate a directory are find first file and find next file. And these APIs don't take a buffer size. They use default system buffers to actually read the directory and then serve out data from those buffers. get file information by handle EX, you can specify a buffer to it with a particular size. So you can actually pass to it very large buffer sizes if you want, up to 64K, because that's the limit imposed by the file system. So you can use this API to query for directories. There are two information levels in this API: file ID, both directory information, and file ID information. And these two are used to query directories. And the only thing you need to remember is Windows 7 caches the two levels used by this API, while Windows Vista or Windows 2008, they don't cache. So even though you get the benefit of large buffers, you may not get the benefit of directory caching on older platforms. Another thing, I/O cancellation. As I said before, when you're running your applications over a WAN link, responsiveness is really, really important. So if you are talking about a satellite link with a second delay, an operation can take one round trip can take up to 1 second to complete. So cancellation becomes very important. You want to be able to bail out based on user input. Now, starting with Windows Vista, we put in a lot of work into the platform to make a lot of these calls cancelable. So we have the cancel synchronous I/O API call it's a Win32 API. You can pass to it a thread handle. And if the thread is actually blocked in a synchronous API, like even create file, it will come out immediately. The create will get canceled, and the thread will be released. We have seen from our Watson metadata logs, very often, in a lot of cases, create file calls or any other call which indirectly involves a create file. This is the #1 cause of hangs. The primary reason being create file calls can often result in connection establishment, authentication to the server, and delays associated with these things. And so create file is a call very susceptible to long delays, and we do have the ability to cancel this. If you have used the command prompt in Windows Vista, in fact, if you do like a dir to a non-existent server, you can just press Control-C and it will come out. If you try the same on an older platform, it will just keep hanging there till it times out. So if you're writing your application, do support cancellation. Use overlapped I/O whenever possible. With overlapped I/O, you have the additional benefit that you can selectively cancel a particular overlapped operation or all overlapped operations on a handle. So you can use the cancel I/O EX API to handle the cancellation. And overlapped I/Os don't block, so it frees up your thread to do other tasks like handling user input or stuff like that. And very important guideline, don't do blocking network I/O calls in your main application thread, especially if it's a UI app. You don't want to be doing any blocking network calls in your main UI thread. It will result in hangs, poorly responding applications. And one caveat with pipelining, this is mostly oriented to throughput oriented apps. If you pipeline too much of data, these requests get queued either on the server or on the client or on the network, and it'll be a while before they get completed. So you want to pipeline the right amount of data. And typically how we do this in the platform is we measure the response time of a request complete, and we try to keep it within a certain bound. So if responses start taking longer and longer, you kind of throttle down your application so that you reduce the pipeline depth. So important to remember to not to pipeline too much data. Let's look at a quick summary. Throughput-oriented applications fill the network BDP by issuing as much I/O as possible. Use asynchronous I/O and large I/O chunks. Use copy file or copy file EX if your application permits that, and you can operate on the file locally. It's sometimes a lot efficient to do that rather than to operate on it online. And use threading, multi-threading when operating on a large number of small files. When you're doing a lot of synchronous calls, the only way to parallelize them is to do multi-threading. You can't get the benefit of overlapped I/O. And for interactive apps, use the handle-based APIs whenever possible because it avoids additional round trips to the server. Help the system to cache data effectively by monitoring your open patterns. So avoid multiple open handles when you're writing new apps, and avoid things like byte range locks, write-only opens, and things which we described earlier. Watch out for your metadata queries. They're not free, and they can involve more than one round trip. So watch out for this and use those that are cached by the system to your. And finally, support cancellation in your applications. Very important. Otherwise, people will be really frustrated. They will click the red X and kill your application. So support cancellation. These are things which we have learned. We have been investigating since Vista, and we have been constantly improving the platform to provide added benefit. We are modifying the applications shipped with Windows and even outside of Windows, like Office, to adhere to some of these guidelines. Now, this is a quick overview of the tools which we use to actually monitor the applications. Process Monitor, very useful tool. You can use it to monitor file access, registry access, thread process, DLL loading, pretty much anything. So this tool is really useful, and it can really give you a lot of insight into how your application opens files and accesses files. It's available. There's a website. And the second one we use very often is a network sniffer. We use Netmon 3. This is also freely available, and you can look at the website. And it has parsers for a lot of protocols, including SMB and SMB2. And we constantly keep the parsers up to date to incorporate any new changes. So very useful tool. And you can look at the process monitor trace and the Netmon trace and see how much optimization is happening under the covers in the platform. And well, there are other network monitoring tools like Wireshark and etc. And the one we support is Netmon 3, and in fact, it has a very nice parser language. It's a scripted language, and you can write your own parsers and stuff. So it's a very interesting tool to look at. So that brings me to the end of the talk. So be aware that your application will be used over a slow network, even though you didn't design for it. It will surely get used over a WAN link in going forward. And we are constantly making improvements to the platform. And a lot of the guidelines I presented here, they're not just for files. You can use these, specifically the pipelining. You can use these in a lot of applications which do I/O over a WAN. And use the APIs provided to your advantage. And it's very important, I think, to understand at least part of how the system works, so that you know when you do a certain operation, you know what goes on underneath the cover, so you can adjust your programming patterns or your API usage to best help the system to perform the operation most effectively. And that's all I have. So please fill out the evaluation sheets, and recording will be available within 24 hours, I believe. That's all I have, and I want to open up for questions. So you can either ask me here, or I'll be down in the lounge area by the Windows Server 2008 R2 booth, or the Hyper-V areas. One of those two areas, I'll be there, and you can meet me and ask me questions. All right, that's all I have, and thank you very much.